Most digital content pipelines today are anchored to a centralized architecture. Creators rely on cloud SaaS platforms as the primary engine for generative production. Look closely at these platforms, and the underlying business model becomes obvious. They operate as simple API wrappers, acting as a middleman between the user and the language model, and they charge recurring monthly fees for the privilege of routing your data. The structural inefficiency here is severe. Users pay premium subscription rates simply to access foundational large language models, and that access is heavily metered by the platform's arbitrary tier limits. VibeTube AI version 1.1.1 is engineered to bypass this entire structure. It is a standalone Windows desktop application, meaning it shifts the execution environment from a remote server farm directly to your local hardware. This local execution is built around a protocol called Bring Your Own Key, or BYOK. Instead of using a developer's shared credentials, you input your own personal, free Google Gemini API key. By removing the cloud middleman, the software communicates directly with the language model. You are no longer subject to a third party tracking your queries or throttling your output volume to protect their server costs. Routing directly to Google AI Studio neutralizes standard SaaS overhead. A single URL input deploys a 19-node orchestration matrix, generating comprehensive production assets simultaneously. Moving the compute authorization from a rented cloud server to your own desktop redefines the economic control of the content production pipeline. You own the engine rather than renting the output. The system pipeline begins with data ingestion. You paste a target URL from any web page into the application interface. Standard web scraping routes that URL through third-party cloud servers. Those servers parse the data, extract the text, and log the user's inputs, introducing a significant data security vulnerability. To close this vulnerability, the application utilizes a local instance of a parsing library called Cheerio, executing the extraction process entirely on your machine. This flowchart illustrates the Cheerio process. It takes raw web page code and strips away the document object model. It filters out navigation, ads, and styling tags to isolate core text. What remains is a minimalist, track-free payload, perfectly formatted for a language model. Confining data ingestion to the local desktop ensures operational security. The source material is processed and sanitized before the data ever leaves your machine to reach the artificial intelligence model. Next, the system must transmit that clean payload to the Google Gemini API. Subscription SaaS tools require the developer to store master API keys on their centralized servers. If their database is compromised, the routing infrastructure is compromised. VibeTube AI secures your personal credentials using the keytar protocol. This mechanism encrypts your Gemini API key locally. Keytar integrates directly with your computer's native operating system keychain. The sensitive credential never sits in plain text within the application folder. It is locked within the OS-level security architecture of your own hard drive. Look at this routing map. By securing the key locally, the desktop node establishes a direct, unbroken line to the external API cluster. The request physically bypasses the developer's centralized servers. Because the developer is bypassed, they cannot apply a markup to the API usage. A live header widget tracks the actual compute costs in real time, pulling usage metadata directly from Google. It calculates the exact volume of tokens consumed and true dollar spend per session. You see the financial impact immediately. Without a third-party margin, the cost drops to functionally zero. Coupling the operating system keychain directly to the API layer removes the financial friction of AI generation. A punitive recurring monthly expense becomes a negligible fixed cost. With the secure connection established, the clean payload hits the application's core orchestration engine. The engine takes that single input and splits it into 19 distinct, concurrent generative pathways, processing multiple prompts in under 45 seconds. This diagram maps the orchestration matrix. The central mode pushes data to output terminals, handling foundational discovery algorithms. It writes algorithm-optimized titles, retention-focused descriptions, and structured timestamps, while simultaneously generating exact metadata for search indexing. It outputs 15 to 20 targeted YouTube tags and a cluster of trending algorithmic hashtags. Another terminal constructs the structural video script, outputting a collapsible teleprompter-ready outline broken down into precise hook, body, call to action, and outro segments. These foundational assets are engineered to satisfy the search and recommendation algorithms of the primary video platform. While those video assets are processing, parallel nodes adapt the core narrative into specific constraints for other networks: a 280-character post for Twitter, a hashtag-heavy summary for Instagram, and a professional post for LinkedIn. Executing 19 distinct tasks concurrently removes the necessity for specialized personnel. The software outputs the strategic alignment of an SEO specialist, a scriptwriter, and a social media manager simultaneously. Beyond text generation, the matrix extends to multimodal design. The outer nodes engineer prompts for external AI generation tools. The NotebookLM audio protocol node analyzes the source URL and constructs a highly specific prompt. It defines the exact persona, tone, and topic constraints needed to generate a broadcast-quality podcast audio overview. Another node engineers visual directives. It calculates shot sequencing, visual transitions, and aesthetic constraints formatted specifically for Luma and Runway cinematic video generation. Look at this prompt interface. For static thumbnails, the matrix calculates mid-journey ready compositions, specifying subject placement, lighting logic, and layout constraints to maximize click-through rates. Once the initial 19 nodes complete their cycle, the SQL engine becomes available. The application retains the context memory from the initial orchestration run. It uses that existing knowledge base to architect entirely new follow-up video concepts, chaining them together with coherent narrative progression. By generating structural prompts for external audio, video, and image generators alongside its own text outputs, the application functions as a technical architect for an entire brand ecosystem. We can now measure the total economic efficiency of this decentralized architecture. This data table contrasts the pricing models. The standard SaaS wrapper escalates from roughly $1,100 in year 1 to over $2,300 in year 2. The BYOK desktop application requires a single fixed cost of $49.99, with a year 2 cost of $0. That cost reduction is paired with an increase in volume. The subscription service typically yields 2 or 3 content types, while the local matrix yields 19. In terms of human capital, this single localized system mimics the concurrent output of a 6-person production pod, a labor overhead that traditionally costs upwards of $500,000 annually. If a creator cancels a cloud subscription, they immediately lose access to their tools and their historical data. A downloaded sovereign executable remains functional indefinitely, immune to server outages or subscription lapses. The bring-your-own-key architecture dismantles the recurring revenue models of centralized platforms. By securing the infrastructure on local hardware, systems architects gain a permanent, unmetered production engine.